Okay, welcome back, Physics 30. This is the sheet entitled 2-1 Reference Frames and Displacements. If you can find that, we'll take a look at it. Alright, so we looked at that 1960s video that showed reference frames, so this is just going along with that. So any measurement of position, distance, or speed must be made with respect to a reference frame or frame of reference. So kind of a starting point. For example, while you're on a train traveling at 80 kilometers per hour, suppose a person walks past you towards the front of the train at a speed of 5 kilometers per hour, such as in this diagram. You're sitting down here, someone's walking by you at 5 kilometers per hour. The whole train itself is going 80, but this 5 kilometers per hour is the person's speed with respect to you on that train. So you're part of the train, so with respect to the train itself, the inside of the train, that person is moving 5 kilometers per hour. But if someone was outside watching the train go by, this moving person would have a velocity or speed, in this case, of 80 kilometers per hour plus the 5 kilometers in the train, so a total of 80 kilometers per hour. So it's always important to specify the frame of reference when stating speed. Simply saying the person is moving 5 kilometers per hour doesn't tell you enough. Okay, because 5 kilometers per hour with respect to what? So you'd have to say with respect to the terrain, and that way you'd be indicating what your frame of reference is. In everyday life, we usually mean with respect to Earth automatically, without even thinking about it, because we're attached to the Earth. So usually when we see a car go 100 kilometers per hour, usually it's automatically with respect to Earth. But the reference frame must be specified to avoid confusion and later on. Okay, so that is what a reference frame is. A frame that you're referring to when you're saying something about an event or about motion itself. Alright. The next page I'd like you to turn to is the one that has the forces on it, and specifically we're going to look at 4-2. So Newton's first law of motion. So what is the relationship between force and motion? Aristotle believed that a force was required to keep an object moving along a horizontal plane. To Aristotle, the natural state of an object was to be at rest, and a force was believed to be necessary to keep it in motion. Furthermore, Aristotle argued the greater the force on the object, the greater the speed. And this makes sense because we can see this happening every day. In order to get something moving, we have to push it. In order to keep it moving, we have to push it as well. So it seems logical. But 2,000 years later, Galileo disagreed. He maintained that it's just as natural for an object to be in motion with constant velocity as it is for it to be at rest. To understand Galileo's idea, consider the following observations involving motion along a plane. To push an object with a rough surface along a tabletop at constant speed requires you to exert a force on it continuously. That makes sense. To push an equally heavy object with a very smooth surface at the same speed wouldn't require as much force. If a layer of oil or lubricant is placed between the surface of the object and the table, then almost no force is needed to keep it moving. So for this, the best idea we can think of this is an air hockey table. An air hockey table is close to being frictionless. If you push that puck just a little bit, it keeps on moving, even by itself, moving at a constant velocity until it hits the other side or it comes into contact with some other force. So notice that in this case, each successive step requires less force. As the next step, we imagine no friction, and that the object does not rub against the table. So if we had a perfect lubricant between the object and the table, you realize that once started, the object would simply move across the table at constant speed with no force being required. So if we had a frictionless case, that would happen. A steel ball bearing rolling on a hard horizontal surface would approach that situation. So does a puck on an air table, in which a thin layer of air reduces the friction to almost zero. So, and of course we don't realize it. We don't realize that there's always friction present, so we have to exert a constant force to keep something moving because of friction. But if we did away with friction, then a little push and the object would keep moving on forever. Such as in space. If we're looking at a lack of air, a vacuum area, if you throw a ball, it would continue on forever. It was Galileo's genius to imagine such an idealized world, in this case one where there is no friction, and to see that it could lead to a more accurate and richer understanding of the real world. This idealization led him to his remarkable conclusion that if no force is applied to a moving object, it'll continue to move at a constant speed in a straight line. and moving at a constant speed and moving in a straight line, that indicates constant velocity. Velocity is speed with a direction. So if we're moving at a constant speed in a straight line, that is constant velocity. So if we had no friction, this would happen. An object slows down only if a force is exerted on it. For example, friction. The force pushing the two objects together, the force that's working against you. Galileo thus interpreted friction as a force akin to ordinary pushes and pulls. To push an object across a table at constant speed requires a force from your hand that can balance the force of friction. So once the book is moving, you only have to supply enough force equal and opposite to friction to keep it moving. When the object moves at constant speed, your pushing force is equal to the friction force. But these two forces are opposite. So the net force on the object would be zero. So these forces would balance each other out, so the object keeps moving. This is consistent with Galileo's viewpoint for objects move with constant velocity when no net force is exerted on it. So if this force cancels this, it moves at constant velocity, which is what happened. Upon this foundation laid by Galileo, Isaac Newton built his great theory of motion. Newton's analysis of motion is summarized in his famous 3 laws of motion. In his great work, The Principia, Newton readily acknowledged his debt to Galileo. In fact, Newton's first law of motion is often called Galileo's law of inertia. So every object continues in its state of rest. So if it's something at rest, it stays at rest unless a force applies on it. Or stays in uniform velocity in a straight line unless a force acts upon it. Okay, so that's Newton's first law. An object at rest stays at rest, an object in motion stays at motion with uniform velocity until another force acts on it, such as friction. The tendency of an object to maintain a state of rest or of uniform velocity in a straight line is called inertia. As a result, Newton's law is often called law of inertia. All right, an example here, our school bus comes to a sudden stop and all the backpacks on the floor slide forward. So it'd look weird if it was a windowless bus and you're just riding along and all of a sudden everything goes flying forward. It could seem to be a fictitious force, and of course that bus is accelerating, or in layman's terms decelerating, but those objects in motion, the backpacks, want to stay in motion, so they're continually moving forward, but the bus is in fact stopping. So so if you look here by Newton's first law, the backpacks continue their state of motion, maintaining their velocity. The backpacks slow down if a force is applied, such as friction of the floor. Okay. Lastly here, inertial frames. This was alluded to in that 1960s video as well. Newton's first law does not hold for every reference frame. For example, if your reference frame is an accelerating car, either speeding up or slowing down, you would see weird things happen in the car, such as cups resting on the dashboard may move towards you if you slam on the brakes and decelerate. And that's because of the inertia of the cups themselves. So in that case, you were actually speeding up and the cup wants to stay at rest, so it falls on your lap. Or if you slam on the brakes, something in the back of the car would come flying to the front because they're continuing their state of motion as well. So quite often, and in that video, they're called fictitious forces when we have acceleration coming into play. So Newton's first law does not hold for acceleration or accelerated frames of reference. Physics is easier in reference frames in which Newton's first law does hold, and they are called inertial reference frames. And for the most purpose, we will make the approximation that a reference frame fixed on the Earth is an inertial frame. Okay, so it's moving at a constant velocity, or it's simply not moving at all with respect to something else. Okay, so it's just the accelerating reference frames where we have wacky things happen. All right, so that'll be the end of that video. We'll see you again for the next one.